Welcome to our presentation of Solid Mechanics by Jordan, Corey, Neil, and Dane. Solid mechanics can be defined as the study of load-carrying members with respect to forces and deformations, with the key purpose being to determine stresses, strains, and displacements. In this video, we will be primarily concerned with two concepts in solid mechanics, stress and strain. Stress is a force per unit area, thus it has the same unit as pressure, for example, pascals or pounds per square inch, but it is more complex than pressure as it varies due to direction and the surface that is acted upon. Now that we know that stress is a force per unit area, we can define it with a formula. We know that normal stress equals normal force divided by the cross-sectional area, and we can use the equation sigma equals F sub n over A sub c. Strain is the amount of deformation an object experiences compared to its original size and shape. It is a dimensionless quantity. Thus we can also define axial strain with an equation, as we know it is equal to the amount of displacement in the axial direction divided by its original length. The equation epsilon equals delta over L represents this relationship. Now we can move on to a practice problem.
Now that we've gone over the basic concepts of solid mechanics, we can move on to a practice problem. The practice problem we're going to do involves a hollow circular aluminum post, which supports a compression force of 26 kips. Now 26 kips is a unit of pressure. It's also equal to 26,000 pounds, because 1 kip is equal to 10,000 pounds. So we can substitute 26 kips for 26,000 pounds. Now, the outer diameter of the aluminum tube is 6.5 inches. The inner diameter of the aluminum tube is 3.5 inches. And the overall length of the aluminum tube is 16 inches. Now, due to this compression force of 26,000 pounds, the post shortens by 0.012 inches. This is due to it being compressed, and it literally shortens and deforms the overall piece of tubing. Now, we are asked to find the compressive stress in the post as well as the compressive strain in the post. Now, this is a fairly simple problem because it's more or less just plug and play. We know that the compressive stress, which is represented by the symbol sigma, lowercase sigma, is equal to force over AC, which is the cross-sectional area, meaning the difference in between the two areas of the circles up top. Now we can expand this out to be force over the specific cross-sectional area, which would be pi over 4 times dimension 2 squared minus dimension 1 squared. That's just the outer diameter subtracted by the inner diameter. The reason we did pi over 4 is because that's due to the area of a circle formula. We just simplified it in order to make it easier for us to solve and enter in our calculators. Like I said, the force is 26,000 pounds, so we can substitute for F. So we have 26,000 pounds. And we divide by our cross-sectional area, which is pi over 4 times d2 squared, which is 6.5 inches squared, minus 5 inches squared. And this gives us a solution of 1,919 psi, or pounds per square inch. Now, like I said before, compressive stress is has a unit of pressure, so that's how you know this is correct, because you have a pounds per inch squared. Pounds per inch, sorry. The compressive strain is equal to the ratio of the displacement of the object, which is 0.012 inches, to the overall length of the object starting, which was 16 inches. So our compressive strain, which is represented by this variable is equal to delta, which is our deformation, over L, which is our overall length. Now delta, as we've stated before, is equal to 0.012 inches, which gets divided by 16 inches. Now, as we said before, the reason we don't have units for compressive strain is because our units actually end up canceling out. So we're just left with 0.00075 inches over inches, but we don't need the unit, so we just have 0.00075 as our final answer.
In this CAD model, we can see the same practice problem actually being done now with real rendering and animation.
Following our practice problem, we thought it would be beneficial to observe some other situations with compression using Autodesk Inventor finite element analysis simulations. With a rectangular prism, deformation from compression will push out the sides and center the force, the most deformation, in the middle of the X, Y, and Z axes, known as the X, Y, and Z bars. With a cylinder, deformation from compression will bulge in the center of the cylinder, just like the rectangular prism. However, as a whole, the cylinder will distribute the weight more evenly because each point on opposite sides are an equal distance from the center axis. If revolved around the Z-axis, X, Y, and Z bars are the same as with the rectangular prism.